Good afternoon, and welcome to today's webcast, Safeguarding on Robots and Robot Cells, sponsored by Schmersal. My name is Travis Hessman. I'm the Chief Editor and Content Director for New Equipment Digest. And before we begin today's presentation, I just want to explain how you can participate. First, if the slides or audio stop responding for any reason, first step is to press the F5 key on your keyboard. That will refresh the webinar console. And there's a toolbar at the bottom of your screen that includes a help icon that'll help you out if you need any further assistance. Now, please note we do welcome your questions during today's event. To submit your question to today's presenter, just type it into the Q&A window on the left side of your screen and then hit the Submit button. We'll be answering as many of those questions as possible during the Q&A session that will follow the main presentation. And today's session is being recorded and will be available on the NED, EHS Today, and Machine Design websites within the next week for you to review. And of course, you'll be notified by email when that archive is available. Also, if you note on your console right now, the Schmersal logo is hot linked. If you'd like to visit their website during this webcast, you can just click on that logo and a new window will open, which means it will not take you out of the webinar. All right, now we've gone over that. I'd like to welcome our speaker today. Mike DeRocher is a TÜV certified functional safety engineer for machinery. His 20-plus years of experience include controls engineering to design, build, and integrate full machine control systems. His safety experience led him to help corporations develop corporate safety standards, perform machine safeguarding risk assessments, machine safety training, as well as implementation of safety systems for all aspects of machinery, including electrical, electronic, pneumatic, hydraulic, and mechanical. And with that, Mike, I'll turn the floor over to you.
Thank you, Travis, and good morning and good afternoon to those all around the area here. Thanks for attending today. I know this is going to be somewhat of a tough subject, especially to cover in an hour when we talk about safety in reference to robots and robot cells in particular. So not that we're going to be able to hit every single possible point because everything really stems from the robot risk assessment. But what we wanted to try to cover today is some of those key points that often seems to be missed or overlooked by many people when they're looking at having a robot cell installed or looking at existing robots and robot cells, and wanted to try to cover some of those points. So the topics we're going to cover today, when you think about what you see in that picture there of a traditional robot, and later on toward the end we'll talk about collaborative robots a little bit, but just guarding around a robot. And one of the key points is knowing those relevant standards. What standards applies to the robots and robot cells and where to get that information. But then that what really leads you into that next bullet point is understanding what the robot's doing. What is the job? What are the hazards associated with it? How are you getting access to that area? How is the robot being taught? What are the needs for productivity? And being able to get the standards together, understand what those limitations are, and knowing what the hazards are in the area, because the hazard is not just the robot. And you may hear me say that a few times throughout this seminar. The robot is one piece of what is being done. You have things like the end-of-arm tooling. You have auxiliary equipment in the robot cells, whether it be conveyors or additional machinery that the robot is loading and unloading parts into, picking from, stacking. There's going to be other hazards associated with it. So one of the common misconceptions is you hear robot, well, the robot is the hazard. Well, that's one of the hazards. You have to look at the entire cell and not just the robot arm itself. And that's what's going to really lead you into your guarding principles, because it's going to stem back to the risk assessment of the robot and the robot cell. and more importantly, get you into the actual safety controls, whether it's the robot controller, external from the controller, what's leading you to that safe condition for proper interface. So knowing the standards, and I didn't list all of them up here, but some of the core ones as a takeaway for everybody listening is really love seeing that the standards organizations have gotten more harmonized globally. And it's not just pods around the world that everybody does things completely different. We are so far harmonized with the robotics standard that it's almost, and if not practically interchangeable, whether you're following the ANSI RIA 1506, the ISO 10218 listed there, or the CSAZ 434. They're all the standards revolving around the robots. And you're going to hear me talk a little bit more about some of the content of these standards. But when you got the 1506 for robot and robot cells, or 08 for mobile robots, but there's also things like the technical reports, the TR 15306, 406, 506. What are those technical reports? They're things that are dealing with risk assessment specifically on robots and robot cells. It gives you a good guide to go by. Safeguarding on robot cells, the application of the standards to the robots, and even getting into the collaborative robots and force measurements and things of that nature. So grabbing a hold of those standards, which are a lot clearer than they ever have been in years, these are great resources and guidelines to go by, and good to have if you're either thinking about getting a robot, have an existing robot cell, or integrating a robot. You want to have those standards and ensure that you're complying with those standards. They're going to give you some great guidelines. So if we look at right now, again, we're just talking traditional robot. You have a robot, say, with a mechanical fence around it and a door for an access area. This is what we see on the floor. We don't see the invisible lines. And I'll get into what I mean by that in the next slide, but when you walk out to a floor where you see a robot, you'll see that robot, whether it be a 6-axis robot, a pick and place, whatever the case may be, a spider picker. Ultimately, what you're looking at is the robot and the fencing around it. And then there's stuff that goes on inside of it. Well, there's actually a lot more to it, and that's where we're getting into making sure you understand the robot functionality and the limitations to it. Ultimately, what you see is robots get defined in spaces. So you have what you see in the big red circle is the maximum space. And when we say space, it's not just the robot arm, it's the robot arm with the end of arm tooling on it. So whatever tool manipulator, part holding, vacuum cups, whatever that tooling is that's on the end of that robot arm, you're looking at the space. And even though we see it as a two-dimensional object here, you have to look at it three-dimensionally. What's the maximum reach capable of the robot with the end of arm tooling? And the gray area is what you see is referred to as restricted space. And then the green area, the operating space. So what do we mean by those two different spaces? We said the maximum was complete reach. Restricted space is usually something where you get safety limits set up, or even hard limit switches, say on the base of the robot, where the robot can only physically go so far before hitting that software safety limit or a hardware safety limit and going into that particular area. So that's going to be kind of your hardware or software max limit in that gray restricted space area. The green area being the operating space is what you program the robot to do. It's going to work with inside that space. So now thinking about what you see in that picture with those three circles with the robot in there, we're going to go onto a slide showing the fencing completely outside the maximum space of the robot. And with that, we are looking at the possible reaching capabilities of that robot. Even if it were to run away, it's outside that maximum space is where the fencing is. So people, we're trying to protect people from the hazards. They're completely outside that area. We don't always see that, though. And what I mean by that is when we advance to the next slide, there are times where you start seeing the guarding saying, hey, the robot has different limits. So we have the restricted space with some hardware safety rated limit switches on the base that the robots only can't travel any further than that. So we're going to move the guarding closer as a result. Can that be okay? Possibly it could. Depends on your safety controls that we'll talk about shortly and what you're doing with that. But even more to the point, we start seeing this now. Well, the robot is only moving from point A to point B. We don't need fencing taking up that much floor space, so we're going to move the guard just to the outside of the operating space of the robot. That can tend to lead into issues, because what if the robot were to run away? You look at where that maximum space is and even the restricted space, that robot can reach over or punch through the guarding as a result. Does that guarding withstand the impact of a runaway robot going full force with the end-of-arm tooling on it? Why is that so much of a concern? Oh, when we look at it and we take that original picture I showed you without the circles that you see on the left there, we don't see circles in real life or those domes because it's the 3D space. We just see the robot with a fence around it. So understanding what the robot's functionality and limitations is so critical to understanding that you have or need effective guarding for your robot. Because in a case like here where you see the size of the guard, the side-by-side pictures there, the guard with the robot looks completely fine until you lay in there what the operating, the restricted, and the maximum spaces are. You tend to find that, hey, in this application, this may not be good, especially if we run into an abnormal condition. Because let's face it, when we talk safety and machine safety and protection of people, it's typically what happens when something goes wrong. It's not always a normal series of events that people intentionally put themselves in the harm's way. Things happen. Robots get out of control. A parameter gets set, and it tells it to go somewhere that it's not supposed to go. And we're going to see some changes in technology as we go through when we talk collaborative robots, but this could potentially be an issue. Why could that even be an issue? Well, let's lay in these pictures here. So the picture on the left, we're showing that robot with the fence, but we're putting some aisleways. Maybe it's forklift traffic or personal traffic. People are walking through or around. Yes, you have an access door for people to safely access the robot. You have proper interlock switches on there. But there you see on the right-hand side the rings where you have the restricted space and the maximum space outside the guard. And where is the person standing right now? They're right on the bottom side of that picture. If that robot were to punch through the guard or have the ability of reaching over the guard or throw its payload or drop something, that could potentially seriously hurt, harm, or kill that person in that aisleway, whether it's the person on the forklift or it's the person just walking down those aisleways. So just because you have a fence around a robot over its operating space doesn't necessarily mean that you have a safe, proper, effective safeguard for that robot and robot cell. what happens when you have guarding outside that maximum space and you have the ability of people getting stuck in there or trapped in there? Because in this particular picture, you have guarding all the way around the robot. That door gets closed. A lot of robot cells, you may see doors that actually have locking switches on there. Do they have a means of egress? Not only that, is there obstructive views? Because why would the door get closed? Sometimes it gets closed automatically. It just swings closed. Other times it requires an operator intervention to rotate a handle. But we have to look at some of the worst case scenarios. Can a person be trapped in there? Do they have a means of safely exiting out? Be able to interlock or shut down or e-stop the robot and have that means of egress? Even if that door is locked, do they have the ability to safely get out of that cell if for some reason they got put into that particular situation? But we were talking the robot with its different spaces being the operating, the restricted, and the maximum space. But what else can be inside that cell? Here you see a picture with the robot with the end-of-arm tooling. Might be like a gripper or a cutting type of blade or any type of tooling on that arm. But what else is in there? Because it could be something as simple as taking a box off of a conveyor and stacking it onto a pallet. But how do those pallets get inside and out? How do those boxes get inside the cell for the robot to stack them? They're coming in on conveyors. Are the conveyors properly protected from reach-in hazards? Are we at the proper safety distance? Maybe the robot is picking parts off of a tray and loading them into a CNC machine, where it's doing machining on a CNC machine and doing a lot of repetitive motions, which is why we're putting the robot in there that's interfacing between the machining centers. Maybe there's more than one. Maybe there's two. There's a load and unload. There's a finishing type of machine. Well, those CNC machines could have automated doors. Well, just because you open up the door in the robot to shut down the robot itself doesn't necessarily mean that the CNC is put into a safe condition. Is that interface, because that CNC has now become part of that robot cell, that integrated cell. Did you take care of that? Maybe the robot's doing some welding. Is the welding equipment safely shut down so you don't have the short circuit from arc welding, for example, or the hazardous of the flashing because the welder was active? Is there other automation type of equipment and machines that are inside that cell as a result? You have to really consider everything that's inside that robot and makes up that cell. What is that robot doing? What is the end-of-arm tooling doing? What are the parts doing? Where are they being loaded and unloaded? What is the real interface that people have to have with that robot? Is it normal routine where they're loading and unloading trays? Is it just pulling stuff off with a forklift? All comes back to understanding what is the function of the robot. Where are the limitations? What are the potential hazards? What is that going to stem back to? You're looking at something like the TR 15306 from the anti-RA community. That document is the risk assessment document that I mentioned earlier when we started. There's a risk assessment process. Go through that risk assessment and understand all the hazards associated with that robot cell. So understanding what the function is and the limitations, that's what's going to help you look at some of your guarding options and what are some of the best options to really work with. It's going to depend on what your company's doing, what your system is doing, what your components are, what you're trying to protect from. So in the case here where you see a picture, there's boxes coming down that's getting packed and sealed, and then the robot's picking it up at the end of the conveyor over on the right-hand side of that screen. I'll zoom in on the next slide so you can see it a little bit better. But it's taking boxes and stacking them and palletizing them. It's putting them on a pallet to send it on its next process, whether it be a shrink wrapper, whatever the case may be, and move on. But what are some of the safety considerations? It could be hard fencing like you saw in the previous pictures. We have safety light curtains and grid. There's safety mats that you put in, which could be on the inside of the cell. Three-position enabling switches. You'll see with any robot controller that you get, one of the requirements is when teaching is activating the three-position enabling switch for certain functions on that robot. It could be laser scanners. There's safety camera systems that shoot above the robot to develop a safety field. You could have things like a double reset where there's a reset button inside the robot cell and a reset button outside the robot cell, so somebody cannot just automatically set up a reset, especially when you don't have line of sight. Somebody walks into the cell, they have to hit a reset button inside, come out, then hit the outside reset button. And this is not the limitations to all the guarding options out there. It's just some examples and some considerations. So as we take a closer look on the right-hand side of that picture, I blew that up a little bit so you can see where that area is. But see if you can take a look at this picture as I talk about it and look at what some of the safeguarding methodology has been implemented into this particular work cell. We have a couple different things, and I'm going to zoom in on each one of those for this particular picture and application. But here you can see a box going in and the robot ready to grab that box and stick it up onto the pallet. So what are the hazards really associated with it? Well, you have the robot with the end-of-arm tooling, which is those clamps, those grippers that are grabbing a hold of the box. You have the robot itself with its motion. You could potentially have a conveyor there, but you see the boxes are going through a light curtain, so you may need a muting light curtain there in order to get there. And you have to look at, whenever you use something like light curtains or light grids, you have to use the minimum safety distance calculations that are laid out. You see that as examples in the robot standards, as well as particularly the reference comes back to ISO 13855 for those. When you look at the hazards associated with that robot, well, it may look like that fencing looks like it's a little close. Well, this could be a robot that has a modern safety controller, which a lot of the manufacturers of robots have now, and have software safe limits that are set up in the controller that you can move that guarding closer to make it more practical and feasible for the cell that you have. So when you zoom in on the first aspect of the guarding, we do have a gated door. So whenever you have a gate for people to gain access to it, you need to make sure you have a proper safety interlock switch. This particular one, you see that red handle on the right-hand side of the gate, has that emergency egress. So if somebody were to get trapped into that cell, they have that red handle so they can safely rotate and get out of the cell as a result. The next one you see is just a fixed fence. It's a perimeter guard, a post with a fixed panel in there, whether it be solid Lexan, a welded mesh, whether it be aluminum extrusion. It's just a fixed perimeter fence. Now, when you look at fence construction, if you have those safe software limits or you're outside the maximum operating space of the robot, you look at standard fencing. But what happens when you move that fencing in closer to where the restricted space is or even the operating space? Well, if that robot were to run away, the issue is that fencing now needs to withstand the impact of a runaway robot with its full force and stay standing and not allow it to break through. The problem is, how do we test that? When you go to look and test with that, I would like to see it. I don't want to be the person that pushes the button that crashes the robot into a fence to make sure it can withstand it. So that gets a little bit harder, which is why you typically see the fencing further out from that robot cell. We look closer to the floor area here. The floor area has a safety mat. So with that safety mat, it could be some of the hazard being, in this case, somebody being able to walk through a light curtain and being on the other side of the light curtain and out of sight. You may need that supplementary protection. And because of that supplementary protection, you don't want that robot to be able to re-engage or be able to turn back on as a result of somebody standing in there. So you may need something like that safety mat or a laser scanner inside that cell to detect presence as a result. Here, I know I only pulled it out in one area, which is where the boxes are going down the conveyor to get picked and stacked. But we have the light curtain in the front side of the screen. So you have two sets of light curtains in there. And breaking those invisible infrared beams there is going to create that robot to go into an interlock condition as a result because of people interfacing with there. It puts the robot into a safe condition before you're able to get to or reach that hazard as a result. I had mentioned double reset, and this is not something that you easily see, but there is a control panel actually inside that light curtain area, which it has the D-stop and some controls, but it also has a reset button on the inside. And then you have a little operator station outside with an E-stop, start-stop, but it has a reset on that unit as well. So in this particular case, if somebody were to break those light curtain beams and they go inside the cell, in order to allow that robot to re-engage again, the operator has to hit the inside one on that control panel, that slope control panel there, come out through the light curtain, and then hit the reset on the outside. That's that double reset. So you can ensure, before you allow that robot to start moving again, you can ensure that there's nobody inside that work cell of the robot. All that being said, there's some really good concepts. It still comes back to the controls, the invisible part. You may see a robot controller on a panel, on a rack mount, in its own enclosure, and the rest of the machines are interfacing with that robot controller. So remember, that is just the controller for a robot. It's not a standalone machine that integrates everything else into it. You're putting CNC machines, you're adding conveyors, you're adding hydraulic equipment, you're doing different things, so the robot controller is one element to it. How do you actually put that robot into a safe condition? I give a lot of credit to the robot manufacturers in today's world because they have really taken advances over the years and not only created things like collaborative robots, but really with the onslaught of technology, they put a lot of safety in the robot controllers themselves. So you don't have to do a lot of things externally anymore. You still have your core safety circuits and schematics, but the robot controllers, a lot of the manufacturers have controllers with proper safeties built into them already. Excuse me. So you can see on this particular robot controller, we have redundant safeties. We have 2 channels of safety for an emergency stop condition, and we have 2 channels of safety for an interlock condition. So when you think about traditional machine guarding, you can have E-stops around your cell. Those E-stops have to put the robot into an emergency stop condition, stop as quickly as possible. That's the E-stop input to the robot controller. Interlocks could be doors, could be light curtains. Where you're not necessarily E-stopping the robot. It could be that those robot controllers have safety-rated parameters in there that you're setting, so you're going into a safe stop, per se, and that's where the interlock channel conditions come into place. What's important about that is when you look at a lot of the robot controllers available in today's market, they'll meet a certain control category for those safety inputs or performance level or skill level that you see that down there. What we mean is you can get a robot controller to say, hey, this interlock dual channel input is rated for control category 3, performance level D, SIL 2 as an example. If you go through your risk assessment and you determine that's exactly what you need, you have that built into the controller and you're running the proper interfaces per the robot manufacturer's installation instructions. You have that capability in there. This is all great. That doesn't necessarily mean you have that on an existing robot and robot controller. Maybe you have a robot that's 15, 20 years old. It doesn't have these dual channel inputs. Does that mean that your robot is not safe? You have to do a risk assessment. What's controlling that robot? What's putting it into the safe condition? If you're just breaking a set of enabling signals, that's not necessarily safe. Are you breaking the motor feeds to it? How was the robot controller supposed to be interfaced back in that time? How are you monitoring that? So existing versus new can be a little challenging. And just because it may have met the standards 15, 20 years ago, doesn't necessarily mean you have a safe environment for personnel. You have to go through that risk assessment process and determine, do we need to update or upgrade our robot or robot controllers? Do we need to upgrade the safety system? Do we have that capability? Is there a controller available that interfaces with that existing robot that has the dual channel safeties that are approved for a category 3 performance level D as an example? That now brings us into discussing some of the latest technology, collaborative robots. I know I was talking a little bit about traditional robots, but I don't want to dismiss what we have with collaborative robots. But there is a big issue with collaborative robots, and the issue is not the robot or the technology, it's the perception of safety. Because you can get some really good collaborative robots out there that perform the function and do different things. But a lot of people think collaborative robots are the end-all, be-all, and they're completely safe. The robot does nothing without the tooling you attach to it. Putting a blunt gripper on there that has no force to it may be perfectly fine. But putting a surgical rated knife on the end of it for doing cutting and slicing, you could have a low force collaborative robot. Doesn't mean that that still cannot puncture your skin in your hand and cause a serious injury because of the knife blade that's on there. So it's important to understand, going back to the whole robot cell, the functionality of the robot. So let's continue talking a little bit about the collaborative robots. The perception that's out there is if I use a collaborative robot, it's safe. I don't need anything else. I don't need additional guarding. I don't need light curtains or safety mats. The robot is safe. We saw all the pictures of people shaking hands with a robot, or we get so immune to it when you think about a lot of the TV shows over the decades have had, whether it be science fiction, talking about robots as, part of the characters, and it's always been in a safe scenario. That's not real life. Yes, collaborative robots can be safe, but it doesn't mean they're inherently safe. It doesn't mean that you don't need additional guarding. A collaborative robot, with its controls and its limitations and the things that you can do, are phenomenal, but you have to consider it with the whole cell and everything else that you're doing with it. So a collaborative robot can help create a safer environment. It can help reduce your overall risk. A collaborative robot does not eliminate all of the risk. You have to look at the system as a whole and what you're doing with it. So we want to change that perception. Collaborative robots are phenomenal. You saw the pictures in the previous. They're out there. people are using them. You want to make sure that they're being used properly and effectively, not just for productivity, but for a safe design. They help you create that safer design characteristic because you can do things in a collaborative robot that is safety rated, such as force and limitations, such as safety stops. And I'll talk a little bit more about some of those collaborative functions in just a minute here. But because of that collaboration, you can actually increase productivity as a result because you don't have lulls and downtime. You can do handoff exchanges if it's done in the right way. So when you look at one of the standards I had mentioned in the beginning, in this case, this is a technical document from ISO. It's 15066. This deals with collaborative robots, and they call out for operations that can be implemented. You know, it doesn't have to be just one. It can be one or more of them. But we have the safety-rated monitored stop, and I'll talk more about each of these ones. Hand guiding, speed and separation monitoring, power and force limiting. But based off of those 4 criteria listed in the standard, you want to make sure that you're implementing it properly, and it still comes back to doing an effective risk assessment on it. So let's talk about the safety-rated monitored stop. Ultimately, a safety-rated monitored stop, in order for you to collaborate with that robot to get into that cell area, let's say it's the robot's guarded on 3 sides, and the one side where you have an interface of exchange of parts, a person loading a part into a tray or putting a tray in, and the robot picking from that. Maybe you're breaking a light curtain. Well, that light curtain in my collaborative robot, it gets wired up to the robot controller to a safety-rated monitored stop. What that means is the robot gets put into a safe condition where it stops. Doesn't mean it de-energizes the motors or does anything else. It just keeps it from moving. And because of the redundancy built into those robot controllers, it puts that in a safe condition. And if it were to all of a sudden start moving for any given reason, then it puts it into a protective stop as a result. So engages the brakes and possibly disables the motor depending on what the robot is, its controller, and what the manufacturer designates as the protective stop. Hand guiding. Hand guiding is also one of those commands where you see more of like a teaching, as an example, when you do robot teaching. Many times, especially in a large cell area, trying to teach a robot from outside the fencing is not very easy to do. You need to get inside there. And because of getting inside there, maybe part of that hand guiding is not only a pendant station, but also maybe grabbing the robot and moving it into position in order to do that hand-guided motion. You can have that as an option where the motors aren't necessarily energized, but you got that encoder feedback for providing that. But you have a pendant station that has an e-stop on it and a 3-position enabling switch to jog the robot into position, move it at a slower speed, reduce risk, things of that nature. That's the hand-guided type of scenario for collaboration. Speed and separation monitoring. What this does is it's an area where the robot can still potentially be moving as a person is entering in a collaborative cell. But what happens is maybe when the robot is in its non-collaborative area, it's doing work, it's working at high speeds. And you're doing that for repetitive motion, but maybe at that high speed, it's manipulating a whole bunch of parts, loading it into a tray, but then that robot is picking that tray up and putting it into the collaborative area. Once it reaches that collaborative field that is designated, the robot actually speeds down and looks at it in that speed, but with the additional of safeguards such as light curtains, a safety mat, a laser scanner, things of that nature, if a person were to enter that cell, it would still put that robot into the safe stop type of position and keep it from moving and reduce that, by reducing the speed, you can also make that collaborative field a lot smaller so you don't have to have as big of an area as a result. So there's more detail in that 15066 standard about speed and separation monitoring. And the last one I think is a big one because this is one of those things that I think you see a lot of examples either in real life or in videos when it comes to power and force ratings on a collaborative robot. I think every one of you at some point may have seen that video or saw somebody demonstrate live. Hey, look, I can walk up to the robot while it's moving and just hit it with my hand and stop it. That's reducing the force and the power limitations. Here's the problem with that. Are they set right per the risk assessment? Have you done any measurements? Have you done force measurements to verify that? Because if they're not set up properly, doesn't mean that the robot is inherently safe with a collaborative design. The force measurements haven't been set up properly. And you can see that being one of the things that are missing in integration, because what you have with those force limitations that are adjustable could depend on the payload. Picking up a 2-pound weight versus an 80-pound weight, there's going to be different potential force-limiting motions in there because of that payload that's in there. But a lot of times people are getting the robot configured for the job and they intend to go back to set all those limitations up to testing. Maybe a time crunch, maybe it got missed, maybe it got forgotten. You need to check that those force limits have been set, and potentially there's technical reports out there about those force measurements and setting them up and doing different things and doing actual test measurements to ensure that you do have safe power and force limiting on that robot. That's critical because just because you have a collaborative robot, if those force limitations are higher than what the human body can take, and this is something that the 15066 committee put together, and you see it one of the annexes, I believe it's Annex A, where it talks about force measurements on the body until it starts causing harm or irritations or things of that nature. So it ends up being extremely important to go through and know what those force limitations are, but also in applying it properly. Just because the force limits have been set up properly doesn't always mean that it's inherently safe at that point. What tooling do you have on there? Just because it's low force, but it's a probe pin that can puncture your finger or your hand or your arm, just because it's low force, it still has the ability to cause serious harm. That's not inherently safe. You have to look at the robot as a whole. So in summarizing it, really get to know the standards, whether it be the RIA 1506, go to like a website like robotics.org, which is the RIA website, has a lot of great information on robots. They're dedicated to the robot industry. Understanding those forces that we were just talking about, what are you dealing with? Don't stop at the robot arm. Is there machinery, hydraulics, pneumatics, conveyors, CNC, automation? What else is in there that poses a potential hazard? Don't just look at the robot itself. What are those acceptable speeds and force limitations? What is going to make that safe? Yes, you have productivity, but once somebody is interfacing with it, what is the safe speed? What are the safe forces? You always need to do your risk assessment. That's with anything that we do, but definitely in particular robot. It's called out doing a risk assessment, not just the responsibility of the end user, the responsibility of the OEM as well. You need to perform a proper risk assessment on the machine. In doing that, because you're doing the risk assessment, you need to implement what is the proper safeguarding. A robot wide open just because it's collaborative doesn't necessarily mean it's safe. You need additional safety measures such as a hard guard still, such as light curtains, such as mats or laser scanners. What are the safeguarding means? Some of the examples we talked about. What has to be implemented and make sure they're implemented. But that also leads us to the controls. Is it properly wired effectively and safely? Do you have a robot controller with the dual channel safety inputs with the safety ratings to it? Is it the safety being done externally because it's an older controller? Is it meeting the proper levels? So at this point, I know I talked a lot for 45 minutes here. I know we can really talk for hours when it comes to robot safety, and there's a lot more to it. But what we really wanted to do, like I said in the beginning, is highlight some of those things that are often missed, overlooked, or not necessarily being perceived properly to ensure you have a safe condition. Because robots, if you haven't had them in your site, they're coming. Robots are gaining more and more strength. Why? It's one of the proper things to do. One, it does help keep people safe from routine, redundant tasks that can cause hazards to people. Robots can work in those hazardous environments. Robots can do a lot of different things, but they don't think like people. People can solve problems that come up. Robots can't. They're just doing what they're programmed to do. So, Travis, let's go ahead and open up to questions at this point.
Yeah, excellent. And actually, we have a ton that have already come in. So you're absolutely right. We could talk about this for hours. We're going to get to as many as we can. We're just going to jump right in. While we're going through them out there, if you could just take a moment to complete the feedback form in the lower left-hand screen, that would get us started. But in the meantime, let's get going. All right, so the first one, I'm actually going to combine a couple of questions that have come up here. It goes back to the very beginning of your presentation on the max restricted operating spaces around a robot. So the question is, who typically defines those areas for a robot? Is it an integrator or a customer? And how do they go about defining those spaces?
Typically, it's a combination of both, but definitely the integrator. But the end user really needs to be involved with that. The maximum space is partly defined by the robot itself. You can only go as far as the robot. So even if the robot has the capability, there's no hard stops. It can go a full 360-degree revolution. Well, with that arm fully out, straight up, straight down at 90 degrees, and rotating around, and you create that 3D dome, well, that's not your maximum space. It's once you put that tooling. So when you have a robot integrator that's putting tooling, because if we take that example of the picture I showed with the two side plates that are picking up boxes from the conveyor to stack on a pallet, the maximum space gets defined by the maximum reach of the robot with that end of arm tooling, and now you know what your maximum space is all the way around. The restricted space now gets defined by primarily integrator, but also the end user. It's an open communication. Everybody needs to know what's going on because we know what the maximum space is. Now, where are we restricting this and how are we restricting it? So if we're putting safety rated limit switches, so instead of the robot swinging 360 degrees, we're only allowing that robot to swing a total of 200 degrees. If it hits at, from 0 to 200, it's okay. But once it goes to, say, 201, that limit switch gets tripped, or redundant limit switches for redundant safety, depending on what's on there. Now, because of that and that rotation goes on, it actually puts the robot into a protective stop or interlock condition. That becomes the restrictive space. The maximum space goes to full 360. The restricted space is now at 200 degrees. But maybe your operating space is what you're programming it into. So maybe that's only running at 180 degrees, but maybe you need that additional restricted space just for programming, testing, troubleshooting kind of thing. So there could be different reasons. But I know the initial question was, who's responsible to figure that out? It's everybody. The end users and the integrator need to be a part of it. The integrator may know a little bit more about it than the end user, especially if the end user is new to robots, where the integrator has been installing and dealing with different robots and robot manufacturers and maybe authorized integrators for certain manufacturers. They know that, but we use the word collaborative, but it is a collaboration. You have to have that open line of communication. Just because maybe the integrator defined it all and they developed the guarding around it, as an end user, you don't want to assume that that's all done, because you need to understand it so you can effectively review it and ensure the guarding is proper. Real life example, I've seen a robot installation where fencing was moved in too close to the robot, but it was definitely outside the operating space, but it was just outside that operating space and the restricted space of the robot. And when we were doing the risk analysis on it and doing the audit and started probing in and asking questions about it, what we ended up finding out was the robot was a modern robot. It had a proper safety controller with dual safety inputs. It had everything it needed. It also had those safety rated soft limits that were built into the controller. The problem we found is the robot was installed, it was being used, it was in full production. Nobody set up the safety rated soft limits. So being able to check that, to know that they're there, because part of the procedure right in the robot manufacturer's manual is you set those safety limits and you tell the robot to go outside those safety limits to ensure it does stay within that limitation, that boundary. So the end user, it's important to really know it, not that you may fully know how to figure it out. You need to understand it, and you need to work with your integrator.
Good. Excellent. And actually, there's another question that comes right on the tail of that, talking about fencing. So the question is it reasonable to account for the strength of the guarding provided? So if the guarding is substantial steel fencing, can't you just, or can't the ability of the fence to stop that robot be taken into account?
It surely can be taken into account. The problem comes into how do you prove that? So unless you have a professional engineer that's structural, that can calculate all the forces with the payload, with the full force of the robot, and the structural integrity, the lag bolt or the bolts that are holding on the fence. Some fences are just clipped in, so they have a lower strength force on there. But being able to calculate that all out, so if that robot were to run away and crash into it, and it cannot break through, it cannot issue projectiles, it cannot reach over the fence, things like that it can't physically harm. Sure, the fencing can now contain the robot. Problem is, how do you provide the proof for that? So if you don't have a structural engineer, your next step is to crash the robot in there. I don't know anybody that's really willing to do that and crash and risk damaging the robot and the end of arm tooling and the guarding just to prove that it was stood in. So it really comes down to you really make that fencing on a traditional robot reach more outside that area or maximum space, and it's not even a question mark. Where those problems come into consideration is because they have a finite space that the robot is going into, and they want the fencing within that finite space because of other machines or walkways like they have there. But then that really gets into, in today's world, definitely use a robot controller that has those safety software limits in there to be able to move that fence in closer. If it's an existing application, that becomes more problemsome because if you don't have the controller that does that, how do you guarantee that that robot is not going to physically puncture through with its tooling and potentially cause harm to people outside the cell?
Right. Got it. Good. All right. I have another one here. This is a long one, so I'll see how it goes. Regarding the double reset systems, this questioner says he's constantly fielding questions about how he can ensure that no one is left inside a cell when the safety function is reset outside the cell, meaning both unintentional resets when the person is not seen inside the cell and intentional when it is reset by another teammate. Is there anything inherent in the double reset approach that can prevent these situations, or are they still stuck with either presence detection equipment inside the cell or administrative procedural controls?
It's going to be a combination of a few different things there. So one of the things with the double reset, it may help reduce the need for the inside type of presence sensing, such as Macs or scanners. The concept is with the double reset is if somebody were to walk inside the cell and they're out of sight, they're behind, let's say, a control cabinet, for example, that an operator can't see. Well, just going up and hitting a reset, it puts them in an unsafe condition unintentionally, okay? So in a case like that, that double reset, it actually forces, in order for that robot to be reset, knowing that a guard has been opened or a light curtain has been broken, it forces somebody to go inside and you hit that inside reset button. But in doing that, you now have full line of sight of that cell, so you don't want to reset it unintentionally because, oh, I didn't know you were in here type of scenario. And you also time limit it. You know, typically you see a lot of the double reset functionalities that people have are usually within about 60 seconds. So you have 60 seconds to hit the inside one, come out, close the door, or come through the light curtain again, and then hit the outside one. If you break that time limit or go beyond that time limit, you have to start that sequence and hit the inside. But it doesn't eliminate the fact of what you referred to in the latter part of your question with intentional. Intentional is always going to be an issue. Even if you had safety mats or laser scanners, if somebody is intentionally going into a cell and telling a coworker to turn that robot on, to turn the end of arm tooling on so I can see what's going on, you have to follow that up with process and procedures, because just because you have a mat in there, what if somebody stands up on a conveyor? Same thing with a laser scanner. Laser scanners are usually about 8, 12, 15 inches off the floor to detect somebody in there. Well, laser scanners can't see everything. That can't be everywhere. So if somebody steps up on the robot base or up onto a conveyor for the sole purpose of bypassing guarding, you're never going to eliminate policies and procedures and training. That has to be put into place. Because if you have a situation where somebody's intentionally doing that, you have a disciplinary issue that you really need to contend with, that somebody is intentionally going into an unsafe condition. There are safe means of doing that, which is why robots and the standards like RIA 1506 and the ISO 10218, why they have things in there for things like robot teaching, why they have things so you can go in there with a free position enabling switch to jog the robot and see what's going on. I have yet to have anybody give me any good justification why they need to be inside a cell when robots running full operational mode. There's absolutely no reason for it. I haven't found anybody give me justification, and I'm sure everybody's heard the horror stories of people getting killed by a robot. And what are the reasons revolved around it? It's usually either the lack of safety, including the policies and procedures and the safeguards that put into place.
Well, excellent. Okay, well, that takes us right up to the top of the hour. It's timed perfectly. So apologies to all of the other questions that came in. We'll get those over to Mike as soon as we can. And with that, we're out of time. So I'd like to thank Mike Rocher and, of course, our sponsor, Schmersal, for this great event. And as a reminder, if you are registered as a group out there, please add your names and emails to everybody who attended in your group to the exit survey. And with that, on behalf of NED, on behalf of NED, EHS Today, Machine Design, thanks a lot for coming out today, and have a productive remainder. Thanks.
Thank you.